question is what we can benefit from multi-dimensional modulation design with respect to 1D like PaLM or 2D QAM constellation. And also I will try to review, give a quick review about the existing multi-dimensional modulation formats and to explain what we can, how to get better. And in the end, I will try to give 2 examples to show how to use attributable information rest to improve the performance of or design the good multi-dimensional geometric shaped constellation. The example 1 is to increase nonlinear tolerance, try to reduce the nonlinear interference, and second one is to try to reduce the optimization complexity because for high dimensionality it's very difficult to design the good constellation. Yeah, so question 1, what is the real multi-dimensional modulation formats? Maybe some people think, okay, we use the 4D because I use 2 polarizations and we use the polarization multiplex constellation. But each is the constellation use 4D space, but it's not real 4D constellation because you are transmitting your signal independently in each constellation, in each 2D. And for real 4D modulation, you should have some correlation between your H2D or H1D or H high dimensionality, and you should be able to transmit the geometry design, the 4D sample. They have some dependency. Therefore, for the real 4D constellation, the 4D sample will not be necessary as Cartesian products of 2D. So this, if you can find the Cartesian products of the 4D constellation, this means it's not 4D constellation formats. Okay, and we can also extend this the definition to 8D, 12D, or even high dimensionalities by using different dimensions. And back to the optical communication. So we know that in optical communication, there are many different dimensions we can use to transmit the signal informations. For example, polarization, wavelengths, modes, and the spatial channels. And information can be transmitted independently, like doing multiplex, or jointly in each degree of freedom. And in previous work, many works has been done in wireless, maybe 40 or 50 years ago. Many different formats have been designed in 2D. And 4D has been used or is investigated in the last 20 years, because in optical communities, people can start to use concurrent communication. Okay. And then the polarization,
we can start now.
Formats and 4D lattice formats has been published and investigated.
Okay.
And
thank you.
So this is some short review.
I'm
and
Jin Xingcai from the
how much gain we can get and why we use multi-dimensional modulation formats.
From Subcom.
And here I show the
Subcom is specialized in the
SNR versus
designing and deploying the submarine systems. We have deployed
with respect to the
200 networks.
And the black curve is shown limit.
The length is enough to circle the Earth more than the
and if you compare, for example, here compare the baseline is 16 QAM, means you have 16 points.
This is a before I start the first like the
1D optimization. For example,
many
the
of my
left one,
colleagues in
the blue curve.
Subcom,
you can also do the 2D optimization. You can see from 1D to 2D.
And also many of the colleagues, they are worldwide.
Yeah, it's not surprised because.
And the outline of my talk.
But if you go to the 4D, you can
start with the overview of undersea systems.
So
and then
the green curve is do the 4D
how to maximize single type capacity
250
systems. Then
because 2D 60
talk about how to maximizing the cable capacity on the constraint of optical power
and the gains
and limited optical power. And finally, going to conclude my talk.
Looks ugly. Will not use that.
We all know the submarine system. They carry
you can make it to be hardware friendly to keep the gain still reasonable. Okay, and if you go to you want to further increase the gain, we can also go to the high kinetic size. You can compare with you can use more points. For example, 16 points in 2D or in 1D. And the blue curve shows the 1D gains and red curve shows the 2D gains. So therefore, the conclusion is here. So if you want to achieve more gains by using multi-dimensional geometric shaping, you have 2 options. First is increase optimize dimensions. And second is increase the kinetic size. Yeah, this is what we can get. And in the last 20 or 30 years, many different 4D constellation has been proposed. And here is a figure to show all the existing constellation by calculating the attributable information rates. And here, if I remember correctly, is calculate the MI, GMI. And all the constellation formats can be found from the reference Eric Aguirre. He has a website we call it the database of constellation. You can find can download the constellation and calculate what you want. For example, GMI, MI, Q factor, anything you want. But most of the formats are optimized, maximizing minimum Euclid distance. It is good for SNRB, but not good for the soft decision factor or the GMI. And all this constellation is not jointly with labeling. So if you go to this website, it's only constellation point. There's no labeling. And this constellation is good, only good for Edmond-Gen channel. So it's still unknown what is good for nonlinear channel. And this research is non-trivial to be solved. And here is a table to show the published gains obtained by geometric shaping with different dimensionalities. With the 2D, it's easy to do, just do some optimization, move the points. You can see more gains can be achieved with the larger points. For example, the geometric shaped 1024 constellation can achieve 1D. I think UCL, DTU did some works during the last 2 years, also with experimental demonstration. And 4D, AD, even larger dimensions has been used to achieve more gains. But another thing I want to point out here is, if you look at the spectral efficiency, when people go to the high dimensionality, the spectral efficiency is very low because it's very difficult to optimize points because the point parameters is become huge to be optimized. And if you consider labeling, it's become untrivial to be solved. And as I know, in the optical communication, the largest dimensionality used is 2040, which published in, I think, the Fujitsu or Mitsubishi a few years ago. And this is the reference paper for the paper in the table. So I just skip here. If you want to know more details, you can contact me. I can send you the slides. And the second part is how to optimize constellation. Here I show example to using GMI to optimize the multidimensional modulation formats because we jointly consider labeling. And so in the first example, I try to show how to design the nonlinear tolerant modulation formats in 4D. As we know that many people has using the model which called the EGN model. EGN model can predict the modulation dependent nonlinear interference. And here the second term, which is dependent on the modulation. So different modulation has different interference. And but in 2D, you can easily use that model for your design, the 2D modulation for geometric shaping. But in 4D, now we have two options. First option is if we have a 4D EGN model, okay, we can just follow in the same strategy to optimize constellation. But unfortunately, now currently we are lack of a good 4D EGN model. And then we have option one is if we look at this 2D EGN model or some other theoretical deviation about the fiber propagation, we find that if the symbol, transmitted symbol have the constant modulus, for example, the QPSK has the constant power, constant modulus in 2D, and if you in the 4D you have a constant modulus in 4D symbol, you can minimize the second term of this modulation dependent noise. So then, following the idea, because we don't have the good model, we try to design nonlinear tolerance modulation. We add this constraint to this optimization. So in this case, we are simplify this optimization problem become the equation one. So we use the cost function GMI. We maximize the GMI as the linear performance, but at the same time, we add the constraint of the constant modulus in 4D. This means all the symbol in 4D have the same power. And by solving this optimization problem, we can find the optimal labeling, which is the constellation format, is the 4D coordinates. And this is the constellation we got by optimizing the spectral efficiency in 4D with the spectral efficiency of 6 bits per 4D. So the spectral efficiency is the same as the PM at QAM. And if you look at this figure, you can see, okay, this is like the 12 QAM in 2D, but actually it's not. It has 64 4D symbols. And here we use a different color and different the size of the circle to show the difference. But in principle, here we can see that if you transmit some points in the same color in X-polarization, and you will transmit you only allow to transmit the same color in Y-polarization. And here is if you transmit the inner ring in X-polarization, you will only transmit the outer ring in Y-polarization. And so here, the 4 times 8 points, you got 32, and otherwise you have another 32 points, which is the outer ring in X and the inner ring in Y. So you have totally 64 points. And in the figure on the right, you can see we plot the Stoker space for this symbol, and all the symbol is on top of a sphere, so it can give an intuition about the power is all the same. Okay, let's look at the performance. So because the constellation is optimized for GMI, so it should have the good performance in linear channel. That's right. And we compare two baseline. One is the PM at QAM. Another is another good constellation designed by Mitsubishi. They call the 42A at PSK. And because the 42 at PSK is designed with constant modulus, so they are not maximized GMI. So you can see here the red curve, we propose this called 4D64 polarization ring switching constellation can achieve the better performance in linear channel. It can outperform PM at QAM by around 0.7 dB in terms of SNR. And it's also better than another baseline. And here we also evaluate the performance in the nonlinear optic fiber channel. Here we show the performance of a multi-span transmission system. And if we first evaluate the effective SNR, we want to see how much nonlinear interference we reduce. And here we can see that for the blue curves and the blue markers is the performance of PM at QAM. It has the variation in 4D symbol. But you can see if we compare, if we compare with this the PM at QAM with another two constellation which has constant modulus, it has a low SNR in same distance. This distance is after 100 span. Each span is 80 kilometers, and so totally we can get about 0.16 dB gain in terms of the nonlinear shaping gain. On top of the linear shaping gain, the total gain is more than 0.8 dB. So this is a linear plus nonlinear gain. And what's this gain can be transferred? It can be transferred to the high GMI or longer transmission distance. So these 0.83 dB gains can be transferred to more than 1,100 kilometers reach increase for this multi-span transmission system. And more details can be found from this our GLT paper published in 2019. And also we do the pre-Swiss result is evaluated by the numerical simulation by using the Monte-Carlo equation. And also we do the experimental demonstration using the same setup. And these results have been published in OECC, which we received the Best Paper Award. And this is our setup. We have 11 WDM channels, 50 gigahertz channel spacing, and 42 gigabaud, and using the single-mode fiber. Each span is 75 kilometers. By evaluate the performance in the experiments, we observe the similar gains as we predict by the GMI or by the simulation. So compared to the PM QAM, we can increase the gain about 13% reach increase. So more details can be found from this OECC paper. Okay, so this is the first example about design modulation to be tolerant with nonlinear interference. And the second example is how to design or simplify the optimization, because if we look at the GMI calculation in here, we find the GMI depends on the constellation size M, and also depends on the dimensionality of the constellation N, and also depends on noise and the constellation points and its labeling. And this calculation is very difficult to be solved if as this m and n increase, because the size of your optimization parameters as the matrix of S is become very large, and the labeling also become large. So that's why in the previous table it's very hard to give a good performance, good constellation in maybe larger than 8D. So the motivation is to reduce the searching space to find good constellation. And the idea we use is we give a definition of the first author labeled constellation. And in this idea, instead of to optimize the 4D constellation in host 4D space, we only optimize constellation in the first author. And for example, we highlighted the green area is the first author because we cannot plot the 4D space, the geometry, so we only can plot in 2D dimensions. And by optimizing the constellation in first author, and later we can mirroring the constellation to other authors, and also can give a good structure. And here we show example is we use this simplified optimization problem to optimize the constellation in 4D with spectral efficiency is 7 bit per 4D symbol. Therefore, you have the totally 128 constellation points to be optimized. But keep in your mind, you also need to optimize the labeling. And here the target SNR is 9.5 dB, and this is the constellation we got after optimization. And also here we show the labeling. And these different color points have some relationship, and it can represent this labeling and the relationship in 4D. And also the details about this paper can be found from our GR team this year, 2021, yeah. And then we compare the two baselines. One is also proposed by Mitsubishi called the 4D288 PSK, but the spectral efficiency is the same as 7 bit per 4D. And at the same time, we also compare with the probability shaping, but we shape the constellation PS6QUAM to have the same entropy of spectral efficiency is 7 bit per 4D. And also we consider their implementation penalty. For example, the short block length rate loss. And here this short block length I list here is we consider the parameters. Okay, so I firstly compare the linear performance. And we can first see that the green one is the proposed modulation. It can outperform than another state-of-the-art 4D modulation formats in linear channel is more than 0.6 dB. But when we compare to the blue curve, which is the PS16QUAM in linear channel, we found the PS can still perform better, even it has some rate loss. So the conclusion is the linear channel PS with the short block length still can perform better than these 4D modulation formats, or similar, because if you reduce the block length down to 32, it was performing worse than the proposed one, but it can be better with larger block length. And then before we go to the nonlinear performance, let's analyze the energy in 4D. So if you look at the 4D symbols for the constant modulus for the modulation format, it should have just the line for all the constant symbols. For example, the 4D288 PSK proposed by Mitsubishi is showed by the green one, only one energy level. But for the PS, or even for the CT-QUAM, you have multiple energy levels. And also for the PS, because you shape the constellation to be have the larger probability for the inner points and smaller for out points, it will introduce some high nonlinear interference because it the larger peak power, and also this we can say this is come from the PAPR. You can see here is the PS CT-QUAM has 5 energy levels and high peak power. But for our proposed one, you can see we only have 3 energy levels, and all the symbols is much closer to this average. The energy is 2. We normalize it to 2. So so we can observe here, we have intuition that the proposed also symmetric constellation can, in principle, have the smaller nonlinear interference. And let's see what we have. So from this figure, we can have the prediction that nonlinear interference, the constant modulus modulation, the 4D 2S PSK, or the previous one we showed that 4D PRS should have the much better performance in 4D OS228 and also in better than PS. So here we evaluate the performance in nonlinear optic fiber transmission, compare all these three type of modulation formats. The parameters we showed on the right, we will not read it, you can just look at it. And we first evaluate the effector SNR versus launch power. So the green one is the constant modulus constellation. You can see it has the larger SNR because it can tolerate with nonlinear interference than our proposed one. But if you look at the PS, it becomes even worse because it's introduced larger nonlinear interference. So we can have the intuition here, the red curve, which we propose one, have the moderate performance linear channel, but also moderate performance